Alright, we're finally on the last page, and this is for a condensed phase, so this is for consideration of liquids and solids. If you are heating a condensed phase, you're transferring an amount of Q to that, but you're probably not going to be expanding or compressing it, and so it's really all about heat, and if it's done at a constant pressure, then this is really a discussion about enthalpy. So let's just use this space to write up. Let's say I have a compound E, and E is a solid, and let's say that I have E as a solid at 5 degrees Celsius, and I'm going to heat it. Okay, so there's my example. I'm going to heat it at a constant pressure. So in the fume hood, on the lab bench, but I'm not going to melt it. I'm staying within that phase. Okay, so say I heat it to, I don't know, 38 degrees Celsius. But the melting temperature is, greater than 38 degrees Celsius, and that's important because I have not undergone a phase transition, no phase transition. And so the question is, what is delta H? Well, delta H is the same as Q sub P, and so it is equal to N Cp molar for that substance times the change in temperature. And so you would have to know what the heat capacity is for E solid. So that would be the molar heat capacity for E as a solid. Because the heat capacity for a substance depends on its phase, it's not the same for a solid as it is for a liquid or as it is for a gas. So that's all there is to this one. And if I'm doing it at a constant volume, it's really as above, except, and you guessed it, that Q sub P for constant volume is equal to N, constant volume, sorry. Let me just scratch this for a second. I would want to do a CV molar, but again, for condensed phases, we don't have a different value. We don't use a different value. So I'm using this, but I want to know, I would like to know if I can use the same value. And we had, I don't know where that went actually. We had talked about the difference, it is on your need to know sheet. We had talked about the difference between delta H and delta U for a solid state or a liquid state, and it's really all about the difference in density. And so for this one, refer to need to know sheet. That's posted as a page separately here on Brightspace, and you will see the difference between delta H and delta U for a condensed phase. You'll need to know the densities at each temperature, and if the density is constant, then we'll take these as the same. This one, not important for the midterm. Chemical reaction, a chemical reaction at constant temperature and pressure. What is the delta H of that reaction? We use Hess's law, as we learned in first year. And if we want to know what delta H is total for that reaction, then we would take the number of moles times the delta H, the molar delta H, and that would give me my whole Q sub P for that. If I'm heating through a phase transition, then I can use this example from up above. I would take my component, say at 5 degrees Celsius, I would bring it, heat it up to, let's say its melting point, which is, I'm going to say 40 degrees Celsius as an example, because here I said it was greater than 38. Then I let it undergo a phase transition at a constant temperature of 40 degrees Celsius, and then, if I'm still heating, then I'm heating the liquid to whatever the temperature is, and I'll say 50 degrees Celsius. The same thing goes for cooling. I'm just going to block this out so that I can continue writing. So the delta H here would be equal to mCp delta T, and that would be for the solid. The delta H here would be however many moles I have times the delta H of melting. Melting. We don't usually call it melting, we call it fusion. And then the delta H here would be equal to N, the molar heat capacity for the liquid, times delta T. And you can add all of these together to get a total delta H. We didn't get to do an example of this in class, but it's pretty straightforward. Okay, so that's that.